this video, we are going to talk about applications of implicit differentiation. And we're going to do one problem from the textbook. It's going to be number 47 here. And the theme of it is production. It says let X represent the units of labor and Y the capital invested in a manufacturing process when 135,540 units are produced. The relationship between the labor and capital can be modeled by 100x to the 0.75, y to the 0.25 is equal to 135,540. So question A says, find the rate of change of y with respect to x. Find dy dx when x is equal to 1,500 and y is equal to 1,000. So we can go ahead and maybe let's just deal with this the way that it is. So we have differentiate the first part. It's going to be 75x to the negative 0.25, y to the 0.25 plus, and then 25x to the 0.75, y to the negative 0.75, dy dx is equal to 0. We're going to have 25x to the 0.75, y to the negative 0.75, dy dx is equal to 75, y to the 0.25 over x to the 0.25. So multiply both sides by y to the 0.75, and we get dy dx is equal to, this is 75y. Divide both sides by x to the 0.75. We get x down there. So that's going to be 25 dy dx is equal to 75 y over x. Dy dx is equal to 3y over x. So let's go ahead and plug in now. Dy dx at 1,500 comma 1,000 is 3 times 1,000 over 1,500 is dy dx is equal to 3,000 over 1,500 is 2. I think it's supposed to be a negative 2. I think that I forgot to, yes, I forgot to, when I subtracted here, this is negative, 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 negative. There we go. Because I have a graph that I'm about to draw for you. that this is a inverse proportionality here, because X and Y are on the same side of the original equation. They're inversely proportional. So it's going to be, both of them have to be positive, but it looks kind of like a rational function where it's always decreasing like that. And we're going to see that as X increases, Y has to decrease. And as Y increases, X has to decrease will be the relationship that they're what we call inversely proportional. Let's go ahead and try and graph this. I'm going to have to do a little bit of manipulation to solve for Y here. So I'm going to write this for part B as Y to the 0.25 is equal to 135,540 x to the negative 0.75 divided by 100. And then I'm going to take that and say Y equals 135,540 x to the negative 0.75 over 100 raised to the fourth power. So I don't care about simplifying right now. I just care about graphing it. So alpha Y equals, let's get a fraction here. And then this needs to be in parentheses so that I can raise it to the fourth power in a minute. So this is going to be 135,540 x raised to the power of negative 0.75. And there's going to be a 100 in the denominator. And this is going to get raised to the fourth power. And I'm going to zoom 0, try and zoom fit. Let's go my window, 0 to 10. X min is going to be 0. Y min is 0. Y max, let's make that 10. So let's make that 1e to the 15th, 1 times 10 to the 15th. And let's make the scale. Let's make it go by 10 thousandths, something like that. So you can see that it's a ever decreasing function like that. In the book, the scale for this is going to be 0 to 2,000 on X and 0 to 100,000 on Y. So 0 to 2,000 X and 0 to 100,000 on Y. And it looks like that. You can see that it's a decreasing function. So as X increases, Y decreases. That would be as labor increases, then available capital decreases because you're going to have to spend capital to get that labor. As capital decreases, then labor let's see, as Y decreases, X increases, right? As X decreases, Y increases. They're inversely proportional. So the relationship here is essentially that Y is inversely proportional to X, or something along the lines of, it's in the general form of x, y is equal to k. And if we had raised both sides to the fourth power, we would get rid of these exponents. We would see that it's kind of related, but it's actually x to the third and y to the first. So this is something called the Cobb-Douglas production function that we just graphed. And this is a very real thing in business. So we wanted to talk about that business application. So there you go. We'll come back next time to discuss our topics in 2.8 with related rates. I mentioned that briefly earlier when we were doing implicit differentiation. And so we'll come back and apply that idea of implicit differentiation to some things called related rates, where one variable, where multiple variables are changing with respect to some variable that we don't see specifically in the problem. Usually it's time. So if I get something like the ladder is sliding down the wall, and the vertical height of the ladder and the distance that the ladder is away from the wall, they're both shifting as the ladder slides down the wall. Both of those are changing with respect to time, but there's a relation between them. They're related to each other, so they're related rates. So that would be an example of a related rate. You're going to do things, though, more with business applications in this class, where revenue and cost and profit are all related to one another, and they're both changing with respect to maybe time, maybe demand, something like that. So we'll come back and we'll talk about those in the next video. See you for the next video.